Hi. In this session, we discuss more on relationship between order of subgroups of automorphism group of a field K and the degree of extension of K over their fixed field. In the last session, we proved that if G is a subgroup of automorphism group of a field K and if F is a fixed field of G, then the degree of extension of K over F is greater than or equal to n. That we proved in the last session. So in this session we proved the other inequality, namely the following. So let G be a subgroup of automorphisms group of a field K and F be a fixed field of G, then the degree of extension K over F is less than or equal to n, which is same as the order of the group. So let us prove this. Let G is equal to sigma 1, sigma 2, etc. sigma n. That means the order of the group is n. With the sigma 1 is identity automorphism of K. And let F be fixed field of G. What we want to prove? To prove that degree of extension K over F is less than or equal to n, where n is equal to order of the group G. So we prove by contradiction method. So let us assume that degree of extension K over F is greater than n. Then the degree of extension K over F means what? Which is same as the dimension of K as a vector space over F. That means the K has a basis over F and that basis contains the degree of extension K over F elements. So since the degree of extension K over F is greater than n, this means that there are more than n number of F linearly independent elements of K. That means there are that means the number of linearly independent elements of K over F is greater than n. So you take some n plus 1 linearly independent elements of K. So let these elements be alpha 1 etc. alpha n plus 1. So consider the system sigma of alpha 1 into h1 plus sigma 1 alpha 2 into h2 plus etc. plus sigma 1 of alpha n plus 1 into hn plus 1 is equal to 0 and so on. Sigma n of alpha 1 into h1 plus sigma n of alpha 2 into h2 plus etc. plus sigma n of alpha n plus 1 into hn plus 1, which is equal to 0. And this system contains n equations and there are n plus 1 elements, variables. And note that the coefficients are what? Sigma e of alpha j. They are all belongs to K because sigma i's are the automorphism of K. So this system has n equations and n plus 1 variables. So the number of equations is lesser than the number of variables. Therefore this system has infinitely many solutions and therefore there are many non-zero solutions for the system. So let one of the non-zero solution of this system be beta 1, beta 2, etc. beta n plus 1. So if you substitute beta 1 in place of h1, beta 2 in place of h2, beta n plus 1 in place of hn plus 1 and so on, in this system we get sigma 1 of alpha 1 into beta 1, sigma 1 of alpha 2 into beta 2, etc. sigma 1 of alpha n plus 1 into beta n plus 1 is 0 and so on. Sigma n of alpha 1 into beta 1, sigma n of alpha 2 into beta 2, etc. Sigma n of alpha n plus 1 into beta n plus 1 is equal to 0. Note that this beta is R and K. So what will happen if all these beta i's, that means beta 1, beta 2, etc. beta n plus 1 are in F? Then we know that sigma 1 is 1. So the first equation gives, because sigma 1 of alpha 1 is equal to alpha 1 because sigma 1 is identity automorphism. Sigma 1 of alpha 1 is alpha 1, sigma 1 of alpha 2 is alpha 2, etc. Sigma 1 of alpha n plus 1 is equal to alpha n plus 1. Therefore, this equation gives you alpha 1 beta 1 plus etc. plus alpha n plus 1 beta n plus 1 is equal to 0. So that this equation we can write it as beta 1 alpha 1 plus etc. plus beta n plus 1 alpha n plus 1 is equal to 0. But you know that beta 1, beta 2, etc. beta n plus 1 is a non-zero solution of the system. That means sum of the betas are not equal to 0. So here we are getting a linear combination of alpha 1 etc. alpha n plus 1 with the sum of the coefficients is not equal to 0. This means what? This means that alpha 1 etc. alpha n plus 1 is linearly dependent. Which is not possible because we assume that alpha 1, alpha 2 etc. alpha n plus 1 are linearly independent. So beta 1, beta 2 etc. beta n plus 1 all beta i's are enough is not possible. So therefore there exists at least one beta I which is not enough. So without loss of generality we may assume that beta 1 is not enough. So you know that there are many solutions or non-zero solutions beta 1, beta 2 etc. beta n plus 1 for the system. Among all these non-zero solutions, choose one solution with a minimal number r of non-zero beta i's. That means in beta 1, beta 2 etc. beta n plus 1 or only r terms are non-zero, rest of the n plus 1 minus r elements are 0 terms, 0 elements, and r is minimum with this property. So after renumbering, if necessary, we may assume that beta 1, beta 2 etc. beta r are non-zero and beta r plus 1, beta r plus 2 etc. beta n plus 1 is equal to 0. All these terms are 0. So and therefore beta 1, beta 2 etc. beta r comma 0 comma 0 comma 0 etc. 0, that one is a solution, non-zero solution of the above system. Now we know that if you have a solution and if you multiply with that solution with a non-zero number, then again that new one is again a solution of the system. So we can assume that beta r is equal to 1. So that means you can divide all the beta 1, beta 2 etc. beta r and 0 0 0, that's a non-zero solution. Divide all these terms with the beta r, you will get to the beta r term will be 1, and the rest of the time again we renamed it as beta 1, beta 2 etc. beta r minus 1. So we can assume that beta r is equal to 1. So therefore the above system, because you know that beta r plus 1, beta r plus 2 etc. beta n plus 1 is 0 and beta r is 1. So above system of equations, this system of equations you can write it as sigma 1 of alpha 1 beta 1 plus sigma 1 of alpha 2 beta 2 etc. sigma 1 of alpha r minus 1 beta r minus 1 plus sigma 1 of alpha r is equal to 0 and so on. And sigma n alpha 1 of beta 1, sigma n of alpha 2 beta 2, sigma n of alpha r minus 1 beta r minus 1, and here beta r is 1 and the rest of the terms will be 0. So this system you can write in short as, because you know that all this sigma 1, sigma 1, sigma 1, sigma 1, this is sigma 2, sigma 2, sigma 2, sigma 2 and so on. So we can write it as in a single equation as sigma I of alpha 1 beta 1, sigma I of alpha 2 beta 2 etc. sigma I of alpha r minus 1 beta r minus 1 plus sigma I of alpha r is equal to 0 for one I varying in between 1 and n. So this equation we call it as 1. But we know that beta 1 is not enough. And therefore you can always find an automorphism sigma k naught in G such that sigma k naught of beta 1 is not equal to beta 1. So because you know that sigma, all the elements of G fixes the elements of F, and beta 1 is not enough, so all the elements may not fixes beta 1. So you can get always one sigma k naught in G such that a sigma k naught of beta 1 is not equal to beta 1. Now apply sigma of k naught to this equation. And you know that sigma of k naught is actually multiplicative homomorphism and additive homomorphism. So you can write this one as sigma k naught of sigma I of alpha 1 into sigma k naught of beta 1 plus etc. Sigma k naught of alpha I of alpha r minus 1 into sigma k naught of beta r minus 1 plus sigma k naught of sigma I of alpha r. This is equal to 0. So this you can write it as sigma k naught of sigma I. We can write it as sigma k naught composite sigma I, sigma k naught sigma I, and so on. Sigma k naught composite sigma I. So you can write it as this equation, same equation we can write it in composite form as 1 for 1 less than or equal to I less than or equal to n, sigma k naught of composite sigma I of alpha 1, sigma k naught of beta 1, etc., which is equal to 0. But you know that sigma k naught is one element of the group G, and sigma 1, sigma 2, etc., sigma n is also an element of the group G. So if you take the composite with sigma k naught with the sigma 1, sigma k naught with the sigma 2, etc., they are also the elements of the group, and which is same as the elements of the group. That means, but in some different order. That means sigma k naught composite sigma 1 may not be sigma 1. It may be some sigma I in between 1 and n, where I is in between 1 and n, because this one is a group. So therefore, for each I, there exists a J such that sigma k naught sigma I is equal to sigma J, because sigma k naught sigma I is an element of the group, and so it will be one of the sigma J, where I is in between 1 and n and J is also between 1 and n. So therefore, this above equation you can write as sigma J of alpha 1, because you know that sigma k naught composite sigma I is same as sigma j, so you can write it as sigma j of alpha 1 into sigma k naught of beta 1. Sigma j of alpha 1, sigma k naught of beta 1, etc. Sigma j of alpha r minus 1 into sigma k naught beta r minus 1 plus sigma j of alpha r is equal to 0. This equation we call it as 2. So you have equation 1 here. So in this equation we are varying I. So in place of I, if you put j, nothing will happen. So we can rewrite it as sigma j of alpha 1 beta 1, sigma j of alpha 2 beta 2, etc. Sigma j of alpha r is equal to 0. That is my equation 1. So equation 2 is sigma j of alpha 1 into sigma k naught of beta 1, etc. So if you subtract this equation, that's the second equation, from 1 sigma j of alpha 1 into beta 1 to sigma j of alpha 1 into sigma k naught of beta 1. So in both the equations, sigma j of alpha 1 is common, so you can write it as sigma j of alpha 1 into beta 1 minus sigma k naught of beta 1 plus etc. So here also you can get a sigma j of alpha r minus 1. But you know that the last term of equation 2 is sigma j of alpha r, and in the sigma 1 also sigma j of alpha r. So that last term get cancels. So you will get there are only r minus 1 terms in this equation, and it is equal to 0. This means that beta 1 minus sigma k naught of beta 1, beta r minus 1 minus sigma k naught of beta r minus 1, this one is actually a solution or a non-zero solution of the above system, because you know that sigma k naught of beta 1 is not equal to beta 1, so beta 1 minus sigma k naught of beta 1 is never be 0. Therefore, this one is a non-zero solution of above system. And this contains less than r terms, non-zero terms, and the rest of the term is 0. Which is not possible because we assume that r is the least number such that beta 1, beta 2, etc. beta r is a non-zero solution of the system. So this is a contradiction. Therefore, our assumption is wrong. Therefore, the degree of extension k over f is less than or equal to n. So in the last session, we proved that this degree of extension of k over f is greater than or equal to n if in the same situation. So we have, combining these two theorems, we get if G is a subgroup of automorphism group of field K and F is a fixed field of G, then degree of extension K over F is same as order of the group G. So we have a corollary to it. So let K over F be any finite extension. Then we can show that the order of the automorphism group K over F is always less than or equal to degree of extension K over F. And equality holds, that means order of automorphism group of K over F is equal to degree of extension K over F are same, they are same, then if and only if F is the fixed field of automorphism group of K over F. This means that whenever the order of the automorphism group of K over F is equal to degree of extension K over F, then by definition K over F is a Galois extension. Therefore, the equality holds means what? K over F is a Galois extension. So, K over F is a, from this we get K over F is a Galois extension if and only if F is a fixed field of K over F. So, let us see the proof of it. Suppose K over F is a finite extension and let F1 be a fixed field of automorphism of K over F. And therefore, F1 is a field between F and K. That means F is contained in F1, contained in K. So you think of automorphism of K over F as a G, and that G is a subgroup of automorphism of K, and F1 is the fixed field of this group G. Therefore, the above theorem says that, this theorem says that the degree of extension K over F and the order of the group are same. So in this case, in our situation, G is equal to automorphism of K over F. Therefore, by above theorem, order of this group, that means order of automorphism of K over F, is same as the degree of extension K over F1. Where, because F1 is the fixed field of automorphism of K over F. But using the multiplicative property of the degree of extension, we can write, because F is contained in F1, contained in K, the degree of extension K over F is equal to degree of extension K over F1 into degree of extension F1 over F. But the order of the automorphism group K over F is equal to degree of extension K over F1. So if we replace this degree of extension K over F1 with order of the automorphism group of K over F, we get degree of extension K over F is equal to order of the automorphism group K over F into degree of extension F1 over F. So therefore, the order of automorphism of K over F divides the degree of extension K over F. Therefore, this number, that means order of automorphism of K over F, is less than or equal to K over F. Degree of extension K over F. That is the first part of the corollary. Now the second part says that suppose the equality holds here. That means degree of extension K over F is equal to order of the automorphism group of K over F. Then this degree of extension F1 over F must be 1. So therefore F1 is equal to F. That means, but F1 is the fixed field of automorphism of K over F. That means F is the fixed field of automorphism of K over F. Now conversely, suppose F is the fixed field of G. That means G is equal to automorphism of group of K over F. Then, because F is the fixed field of this group, by above theorem says that the degree of extension of K over F is same as the order of the group. That means order of automorphism of K over F is equal to degree of extension K over F. That means order of this order of the group of automorphism group of K over F is equal to degree of extension K over F. Therefore, by definition, K over F is a Galois extension. Therefore, the equality holds. Therefore, the equality holds, and since automorphism of K over F is equal to degree of extension K over F, by definition, K over F is a Galois extension. Therefore, we proved that if K over F is a finite extension and order of automorphism group of K over F is equal to degree of extension K over F, then K over F is a, if and only if F is a fixed field of automorphism group of K over F. That means K over F is a Galois extension if and only if F is fixed field of automorphism of K over F. So another corollary to this one is let G be a finite group of automorphism of a field K and F is a fixed field of G, then every automorphism of K fixing F is contained in G. That means if automorphism of K over F is equal to G, so that K over F is a Galois with Galois group is G. So let us see the proof of this. So it is given that G is a finite group and it is a subgroup of automorphism of field K and F is a fixed field of G. So, and therefore the order of because F is a fixed field of elements of G and automorphism of K over F means what? The set of all elements in automorphism of K fixes F, and elements of G also fixes F. Therefore G is a subgroup of automorphism of K over F. Therefore the number of elements in G is less than or equal to number of elements in the automorphism group K over F. Now because G is a subgroup of automorphism of K over F and F is a fixed field of G, we have degree of extension K over F is equal to order of the group G. Because we know that by theorem it says that if F is a fixed field of G, then the degree of extension K over F is equal to order of the group G. So also K over F is a finite extension. We have the number of elements in the automorphism of K over F is less than or equal to degree of extension K over F. This we proved we have seen in the previous corollary. Therefore, the degree of extension K over F is equal to order of the group by this one. Degree of extension is equal to order of the group, but order of the group is less than or equal to automorphism of K over F, and automorphism of K over F is less than or equal to degree of extension K over F. Combining all these things, we get degree of extension K over F is equal to order of G. Order of G is less than or equal to number of elements in the automorphism group K over F, which is less than or equal to the degree of extension K over F. So the left hand side and right hand side are same, therefore these all the terms are same. Therefore the number of elements in the automorphism group of K over F is equal to degree of extension K over F, and that is same as the order of the group. This means that because of this equality, that means the number of elements in automorphism of K over F is equal to degree of extension K over F, means therefore by definition you will get K over F is a Galois extension, and the Galois group of the degree of extension K over F, that means automorphism of K over F, is same as the G. That means G is the Galois group of the extension K over F. That's the end of the proof. So in the next session we discuss about the Galois extension implies splitting field of a separable polynomial. Thank you.